Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hello, good morning everyone. How are you today? So let me introduce myself first. My name is Az-Zahra from Group 7 and it's a good pleasure to be here today. So today my title of presentation is Ethanol Production from Food Waste, and the members of my group are Az-Zahra, Elena Wardani, Winul Khofifah, and the last one is Anissa Purnama Putri Hermawan. Okay, so today we have 3 different articles that we have reviewed before, and the title are: the first one is ethanol production from food waste at high solid content with vacuum recovery technology. Second one is ethanol production from enzymatically dry food waste using enzyme produced on site. And the last one is bioethanol production from food waste applying the multi-enzyme system produced on site by fusarium oxyflume F3 and microbial cultures. So everyone, do you ever heard about ethanol production from food waste? Over the past few decades, the objective to establish national energy independence and to reduce the greenhouse gas emissions have led to the development of renewable biofuel technologies based on agricultural materials. Ethanol is by far the most significant biofuel in the United States, accounting for 94% of all biofuel production in 2012. Ethanol is mainly produced from corn in the US and from sugarcane in Brazil. However, corn and sugarcane are also used as food. Overuse of corn and sugarcane as a feedstock for ethanol production will create food versus fuel competition. Furthermore, increasing prices of corn and sugarcane are the main drivers of the highest cost of ethanol productions. According to the previous studies, corn and sugarcane feedstock costs contributed to 70 until 90% of the total ethanol production cost. So we are going to the first journal. The title of the article is Ethanol Production from Food Waste at High Solid Content with Vacuum Recovery Technology. The authors are Haibo Huang, Nasib Qureshi, Wensu Chen, Wei Liu, and Vijay Singh. The title of the journal is Journal of Agricultural and Food Chemistry, and the year of publications is 2015. So the article summary from the first article is ethanol production from food waste doesn't only solve environmental issues but also provide renewable biofuels. This study investigated the feasibility of producing ethanol from food waste at high solid contents. A vacuum recovery system was developed and applied to remove ethanol from fermentation broth to reduce yeast ethanol inhibitions. A high concentration of ethanol was produced by conventional fermentation of food waste without vacuum recovery system. When the vacuum recovery is applied to the fermentation process, the ethanol concentrations in fermentation broth was controlled below 100 grams per liter, thus reducing yeast ethanol inhibitions. The vacuum fermentation system was modified on the basis of the system reported by CHD et al. It consisted of 3 liters jacketed fermenter, which was sealed and modified for accommodating thermocouples and venting and sampling ports. Slurry was agitated by pedal type brake driven by alternative currents or direct currents motor drive. The vacuum recovery system was connected to the fermenter venting port through a shell valve. The condensate was collected in 250 ml conical flask. Vacuum was generated with a dry vacuum pump at 6.7 kPa. To study the ethanol recovery characteristic under the vacuum applications, Ethanol recovery experiments were conducted. Ethanol recovery experiments were conducted using model ethanol solutions at different initial ethanol concentrations. They are 40, 80, and 160 grams per liter, which cover the possible ethanol concentrations range in the food waste fermentations. After 1 hour of vacuum applications, the ethanol concentration in the model decreased by 9 until 31 grams per liter, depending upon the initial ethanol concentrations in the model solutions. Therefore, the developed vacuum recovery system could be applied to maintain ethanol concentrations in both at low level and reduce ethanol inhibitions. The ethanol concentration in the condensates were 204, 274, and 346 grams per liter, when the initial ethanol concentration in the fermenter were 40, 80, and 160 grams per liter, respectively. This indicates that the vacuum recovery system not only removes ethanol from the fermentation broth, but also concentrates it. And then we are going to the article critique. In the first article, this article is really good. Show the data and experiment completely. The procedure and the purpose of investigation in this article is clearly stated. But the using of words in this article is quite difficult to understand easily by the readers. Okay, the next topic will be delivered by Anissa Purnama Putri Hermawan.
Conclusion Journal 1. In conclusion, food waste at height solid content 35% W per W was used to produce ethanol with and without the vacuum recovery technology. The ethanol conversion efficiency for the vacuum fermentation was 93.6% higher than that for the conventional fermentation at 85.5%. Okay, Article 3. The title of article, Ethanol Production from Enzymatically Treated Dry Food was using enzymes produced on site. The author are Leonidas Mastakas and Pavel Christakopoulos. The title of the journal is Journal of Sustainability. The year of publication 28 January 2015. Article summary. Journal 2. To minimize the cost of ethanol production, the hydrolytic enzymes that are necessary for cellulose hydrolysis were produced in-house using the thermophilic fungus Mycelioptora thermophilia. At the initial stage of the study, production of this thermophilic enzyme was studied and optimized, resulting in an activity of 0.28 fPW per mil in our extracurricular broth. 1. Evaluation of the production of thermophilic enzymes using HFW as raw material. Figure 1. Effect of addition of external nitrogen source A and initial concentration of HFWB on the produced enzyme activity. Then, the effect of the initial solids concentration on the ability of the fungus to secrete cellulosic enzyme was evaluated at a range of 2% until 6% W per W. Cellulosic activity increased when increasing concentration of HFW and it reached 0.28 FPU per mil when 6% W per V HW was used as raw material. Figure 1. On the other hand, the yield cellulosic activity per gram from HFW decreased from 650 FAU per Z to 4.67 FAU and G when the HFW concentration was increased from 2% W per V to 6% W per V. 2. Evaluation of the production of thermophilic enzymes using HFY as raw material. Figure 2. Ethanol production with point and without point inclusion of certification with the thermophilic enzyme solution. During the control experiment without the additional of enzymes, the ethanol concentration was rather low, reaching only 5.78 G per L, which was more than 3 times less than when thermophilic enzymes were added. After 21 of fermentation, which corresponds to 0.28 G per L, figure 2, this ethanol concentration was equal to 11.98% of the maximum theoretically possible based on both soluble and insoluble carbohydrates, and 31.88% of the maximum theoretically possible based on soluble carbohydrates only.
Conclusion Journal 2. The result of the discussion show the possibility of production thermophilic enzyme solution from source-stable HVV. The use of thermophilic enzyme during the hydrolysis of cellulose provides several benefits. While the production of cellulose at home can increase the economic of the process, during high dry matter concentrated HVV fermentation, the use of thermophilic enzyme increased the ethanol production by a factor of more than 3. Journal 3. Title of the article: Bioethanol production from food waste applying the multi-enzyme system production on-site by Fusarium oxycoforum V3 and mixed microbial cultures. Author George Pascolas, Agelius Gencus, Alcaterial Conti, Silsilini Contalesi, Dimitris Kekos, and Doimi Mama. Title of the journal: Fermentation. Year of publication: 2020. Summary 1. Food waste composition. In general, the composition of food waste is complex and includes oil and water, as well as spoiled and leftover food from kitchen waste and market. These substances are mainly composite of sugars, carbohydrate, polymer, protein, starch, cellulose, and hemicellulose, lignin, protein, lipids, and a remaining smaller inorganic part. High moisturizer content leads to rapid decomposition of the organic waste and the production of unpleasant odors which can attract files and books, which are factors for various diseases. The feedstock used in the patient study was provided in dry computational analysis of VW is presented in table 1. Total reducing sugar 4,96 is approximately 0,94%. sucrose 0,51, approximately 0,04, protein 0,33, approximately 0,0, and soluble starch 1,15 is approximately 0,09. The composition of wheat carbohydrate protein makes an excellent feedstock for the production of biofuels and bio-based chemicals through microbial conversion. The physical science contents of the wheat is difficult of being used by ethanol producing microorganisms such chromis surface to multi-enzyme production under solid-state cultivation. To make the enzyme hydrolysis of wheat more cost-effective, the enzyme should be produced on-site from a safe feedstock. CCS has several biotechnological advances such as high fermentation capacity, higher end product stability, lower catabolic representation, and cost-effective technology. SSE is an attric process for filamentous fungus cultivation because the solid substrate have characteristics similar to the natural habitat of the fungi, resulting in improved growth and secretion of a wide range of enzymes. 3. Hydrolysis of wheat 3. Hydrolysis of wheat by the one-side products multi-enzyme system of the oxform V3. Multi-enzyme system of the oxporium of V3 production under CCC on wheat as carbon source was evaluated in wheat hydrolysis of figure 1a. Glucose release applying the oxporium enzyme system was found 33,7 grams divided by liters corresponding to a hydrolysis yield of 47,4, based on cellulose and starch content of wheat. It should be mentioned that glucose release due to plasmin of wheat accounted for 11,2 grams divided by liter. Supplementation of hydrolysis mixture with glucomylase increased glucose release by approximately 25%.
Bioethanol production by mixed microbial culture of V. oxysporum V3 with the yeast C. cerevisiae. The process generally used in bioethanol production are simulation, saccharification, and fermentation (SFF), and separate hydrolysis and fermentation (SCF). In SFF and product inhibition of B glucoside is avoided, and the need for spared reaction is eliminated. In the present study, VW were converted to bioethanol applying SFF process in batch mode. Ethanol production from VW by monoculture of V. oxysporum V3 reaches 16.3 grams per liter after 94 H of fermentation. Can be seen in picture 1a, corresponding to 2.3 grams per liter after 94 H of fermentation. Can be seen in picture 1a, corresponding to 31.8% of the maximum theoretical based on the soluble fraction and the carbohydrate content of VW. When the fermentation medium was supplemented with 20 U per gram starch glucomylase, ethanol titer was 23.9 grams per liter, corresponding to 46.8% of the maximum theoretical. Maximum ethanol production was recorded at 139 H of fermentation, and no further increase in ethanol concentration was found when fermentation was extended to 163 H. But Bioethanol volumetric productivities were in the range of Dow 0.17 to Dow 0.23 gram per liter per age. To improve the sugar assimilation rate, mix culture of V. oxyporum V3 with the yeast as cerevisiae were applied with the same bioconversion setup. The results are present in figure 1b. As can be seen, ethanol concentration at 18 of process was about 18.3 gram per liter in the mixed culture of V. oxyporum V3 with S. cerevisiae, approximately 7.5 times higher than the corresponding value achieved with the monoculture of V. oxyporum V3. Fermentation was complete after 4 to age. Using microbial culture and ethanol production reached 20.6 gram per liter. Ethanol concentration of about 26.8 and 25.1 gram per liter were reached at 18 age when the mixed cultures were supplemented with 20 and 40 U per gram starch of glucomylase, while the corresponding value in monocultures were in the range of 1 gram per liter. Maximum ethanol production of 29.9 and 30.8 gram per liter was achieved at 69 age. Can be seen figure 1b. At the end of all fermentation, glucose concentration in the fermentation broth was lower than 2.0 gram per liter. Volumetric productivities range from 1.0 gram per liter per age mixed microbial culture to 1.5 gram per liter per age mixed microbial culture supplement with 20 U per gram glucomylase. It is evident that mixed microbial culture decreases significantly the time needed for the fermentation to be complete, therefore increasing volumetric productivity. Mixed cultures of mesophilic fungi such as V. oxyporum V3 and then crossed with the yeast C. cerevisiae have been successfully implemented for the bioconversion of sweet sorghum and sweet sorghum bagasse to bioethanol. And next, critic article, Journal 3. The research method in this journal is not explained clearly and coherently. The use of words and analysis in this journal is a bit difficult to read. Conclusion, Journal 3. Bioethanol is a smart solution to address food waste and fossil fuel shortage. The effectiveness of bioethanol can be increased such as by vacuum recovery technology, using enzyme produced on site, and applying the multi-enzyme system produced on site by Fusarium, Oxyporum, F3 and mixed microbial cultures.
Okay, so the presentation of my group today is that. And thank you for your attention. See you. Wassalamualaikum warahmatullahi wabarakatuh.